Okay, good morning everyone. Can everyone hear me clearly? Yeah, excellent. It's a good start. So welcome to my talk, Cracking the Perimeter with SharpShooter. My name's Dominic Chell. I work in the red team for a company in the UK called MDSec, where I mainly focus on the offensive side of security. Day to day, I spend a lot of my time managing and executing our threat intelligence-led red team engagements under the CBEST, STAR, and TIBA frameworks. If you're on Twitter, you can find me on Twitter under the unimaginative handle of @DomChell. So today, for the next sort of 45 minutes or so, I'm going to talk a little bit about the state of play with regards to initial access. The main focus of the talk is on a tool that I developed to streamline payload generation called SharpShooter. I'll include some of the history of some of the advancements, some of the new features that I added as defenders started to respond to it, and then I'll finish off with a few tradecraft tips. So getting a foothold is often one of the most complex parts of a red team engagement. I often find that I spend a lot of my time actually trying to get in, but once we're in, things tend to fly by. There's been a lot of research into lateral movement, into Active Directory, the development of tools, things like Bloodhound, which kind of really streamline the testing process once you're actually in. But with a few exceptions, there's generally been a lot less tooling around the first bit, which is kind of getting onto the network and establishing that foothold. We used to use things like PowerShell quite a lot in our engagements, particularly in any kind of scenario where you could run something like an execution cradle. The reason for this was PowerShell was a great way to kind of get into memory, so you kind of got to evade antivirus. Unfortunately, defenders are now pretty aware of PowerShell, mainly because it's quite easy to signature, both statically from the PowerShell scripts, as well as with things like command line logging. So defenders are looking for things like encoded command and whatnot on the command line. Then also looking for process spawn chains. So for example, if you see a WinWord executing PowerShell.exe, that's probably not a good thing. We also saw the introduction of AMSI, which provided AV engines with the ability to inspect process memory, whereas previously, if you could actually get a script into memory, you generally had carte blanche. Then we kind of saw the rise of sandboxing technologies. We tend to encounter these quite a lot on our red team engagements, things like FireEye or Bromium, where your payloads are actually getting opened inside a micro VM. There's products like Cylance, Palo Alto Traps, which describe themselves as kind of next-gen AV, which focus on prevention, don't rely on signatures. We've also had difficulties getting payloads into environments. People are becoming more aware of the things that they actually need to block on the perimeter. So, for example, we used to use things like HDAs quite a lot, but we started to, as they gained popularity, we started to see companies blocking application HDA MIME type, HDA extensions on their corporate gateways. So we obviously had to kind of move away from them. So overall, I would say in the last couple of years, I feel like red teaming has got harder, which is not necessarily a bad thing because it generally shows that people are getting better. Kind of with this in mind, I started to develop some tooling that would assist us in generating payloads, and that's the main focus of my talk. The tool was named SharpShooter. I released it last year. I've done several iterations of additional features and updates to it. We've used it on quite a few engagements. It's given us some success. It's helped us in bypassing some of these kind of next-gen products and sandboxes, things like Cylance and FireEye, as well as the kind of traditional AV solutions like McAfee and Windows Defender. I released the tool last year. It seemed to be reasonably well received by the security community. It was also featured in the latest Hackers Playbook 3, Red Team Edition, which I thought was kind of cool. So what does it do? Well, it basically allows you to generate staged and stageless payloads for the majority of the Windows scripting file formats, specifically things like HTML applications, JavaScript files, VB script files, Windows script files, as well as VBA and XSOL for macros. When I say staged, what I mean is basically there's a small bit of code that is embedded inside the payload, which is the stager. This will then retrieve the main payload, which in our case is some C# source code. When I say stageless, I basically mean that the full code is embedded inside the script file, and that's what we'll execute when it's run. I included some defensive evasion techniques inside the tool, things like sandbox detection and a technique called HTML smuggling, which I'll talk a little bit about later. So the foundation on which the tool is built is based on a tool called .NET to JScript. This is a really cool tool that was built by James Forshaw from Project Zero at Google. Essentially, .NET to JS provides you with full interop between .NET and the Windows script host through COM. So this basically means that you can take any arbitrary compiled .NET program and embed it as a serialized object that can be accessed through JavaScript or VBScript. So what SharpShooter does is it takes the .NET to JScript loader and the SharpShooter serialized object. It then encrypts it with a random key using RC4. Base64 encodes it and embeds it inside whatever scripting format that you've chosen. It then has a small harness which will decode and decrypt the payload and execute it. In a staged payload scenario, the payload that's executed will actually be some C# source code, and it's retrieved via web or DNS delivery, as you can kind of see on my little diagram here. So when the .NET to JS executes, uses DNS or web delivery to retrieve some C# source code. It then compiles it on the host using the .NET Code DOM compiler and uses reflection to execute it. And that code could be anything. It could be something that stages an implant into memory. It could be Mimikatz. It could be whatever you want it to be. So how do we kind of go about using one of these tools in an engagement? Well, prior to conducting any red team assessment, we invest quite a lot of time in reconnaissance. We really try and understand our target and what their environment might look like. If you're using something like SharpShooter, there's a few things that you might be interested in. Firstly, we might want to know the version of the .NET framework, or even if the .NET framework is installed on the endpoint. The reason for this is that we actually tailor our payload to match that .NET version. So Windows 7 systems, you'll probably find version 3 of the .NET framework. Windows 10 systems, you might find version 4. Secondly, if you want to actually execute something like shellcode on the endpoint, we need to know what the architecture is if we're executing in process. Obviously, the kind of way around this would be to spawn a new 32-bit process and inject some 32-bit shellcode into that. So how do we kind of approach this reconnaissance? Well, it's actually quite simple because most client-side software will disclose quite a lot of interesting information when you interact with it. So let's say we send a user just a very simple phishing email. All they need to do is maybe open it. And what Outlook might do is if we've got an embedded image, something like this, inside our email, when Outlook tries to retrieve that image, it will then send us a bunch of kind of useful information about the version of Office that is installed. So in this kind of scenario, you can see we've got, it says WoW64, which means it's 32-bit Office on a 64-bit system. We've got various versions of the .NET framework installed, and we can see it's actually using Office 2016. So from a very kind of simple email, we're actually able to get quite a lot of good information about our target in advance. How do we then approach getting the payloads into the environment? Well, I mentioned this technique called HTML smuggling. So this is a really clever little trick that was first documented by Rich Warren from NCC Group in his Demiguise tool. And the way this works is you can basically take any arbitrary file and RC4 encrypt it with a random key, embed it inside a HTML file. When that HTML file is opened, it uses the JavaScript web crypto APIs to decrypt and serve the file to the user using the web storage method msSaveblob. This technique is really powerful because what it actually means is all the corporate proxy might see is a HTML file with the MIME type text HTML. Plus, Outlook actually also supports opening HTML files from an email, so you could just send it directly to your target. So I've included a couple of templates within SharpShooter to populate these using HTML smuggling, but you can really dress it up to kind of fit in well with your phishing campaign. I mentioned we need to kind of be aware of sandboxes. So what kind of tricks does SharpShooter use to kind of avoid these? Well, the theory really is that sandboxes use automated analysis to look for bad behavior. If they don't see any bad behavior, then they'll mark the file as safe. So if we're actually able to detect that we're running in a sandbox and do nothing particularly malicious inside the sandbox, then it might end up getting sent through to the user. SharpShooter's got a number of techniques that were inspired by Chris Trunser and Brandon Argvani's Check Please project. So these include things like domain keying. So if we're able to actually figure out what the internal Active Directory domain name is of the company in advance, we can key our payload to only ever actually run on those domain join systems. If we can't figure out the AD name, then maybe we want to just limit the payload to only running on systems that are just on any domain. The reason for this is many of the sandbox appliances can't necessarily be customized. So things like FireEye will come with like predefined guest images. You can't necessarily easily modify these or join them to your internal domain. Then it's also got some bits of functionality to look for various artifacts from sandboxes, so things like MAC addresses that link in with virtualization solutions. It checks whether it's being debugged, that kind of stuff. So let's say we want to try and figure out what the internal Active Directory name is of a company in advance. Well, there's a few different kind of tricks that you can use to do this. The one that we've had a good amount of success with is targeting Skype for Business deployments. So if a company is using Skype for Business as their edge server, which a lot of companies do, you can actually retrieve the fully qualified domain name from that host from one of the headers just by querying it. So we've got an example here where you can see we're querying FireEye's Skype for Business server, and it's disclosing the FQDN of the Skype server. And many companies will actually use that as the actually internal AD name. So here we could speculate maybe that FireEye's internal AD name is fireeye.com. If we did the same thing with Carbon Black, we could see that it's actually disclosing this bit9.local domain. So we could again speculate that Carbon Black's internal Active Directory name might be bit9.local. So when we've got this information, we can then plug it into SharpShooter and actually key our payload to only run on these domains. So let's look at a little example of SharpShooter against Palo Alto traps. Okay, so I have videoed all my demos because I've done talks before. So basically what I'm doing is I'm going to create a stageless HDA file using SharpShooter, which is using HTML smuggling as well. And I'm going to host the file on a Cobalt Strike team server. Then I've got a VM here with, you can see I've got Palo Alto traps in it and it's enabled. And this is what the user would see. They just download the HTML file. It serves them a HDA. When they open the HDA, we get a Cobalt Strike beacon back, where we've got full C2. So we've completely bypassed the Palo Alto traps. Shortly after I released the tool, it started to get signatured by some of the various AV vendors. Actually, Windows Defender created an AMSI signature that didn't just block some of the SharpShooter payloads, but it also blocked the primitive, the exploit primitive that was used by .NET to JScript, meaning that any .NET to JScript payload was now flagged as malicious. This kind of led to the tool being proclaimed dead by Casey Smith on Twitter. I'm not necessarily sure I would say it was entirely dead because I dropped some payloads into VirusTotal last week just to see what the kind of response was, and the kind of default HTML file only had 7 out of 56 detections, and the default HDA file had 18 out of 56, so there's probably still some mileage in it. But regardless, what I wanted to do was actually try and see if I could bring the tool back, see if I could resurrect it. So the first thing I did was to try and look at what Defender was triggering on, and I noticed Defender didn't actually care about the file, the payload, when it was on disk. The signature was actually tied to AMSI, so it was being checked in memory. So AMSI is a security feature that was added in Windows 10, provides a standard interface for file memory stream scanning for any application on the endpoint. The analysis actually occurs at the scripting engine level, which is where the power is really, because it means that the AV engines can get access to the plain deobfuscated code. Currently, AMSI is supported across PowerShell, Windows Script Host, JavaScript, VB Script, and Visual Basic. So here's a little high-level overview of the AMSI architecture. So the way AMSI works is essentially there's a DLL that is loaded into every PowerShell Windows Script Host session. The DLL contains a number of exported functions that allow the container process, such as PowerShell, to call the AMSI APIs. And then this basically allows the registered AV engine on the system to process and scan content. If malicious content is detected, execution is blocked, and an event 1116 is triggered. It's worth noting that the AMSI interface is open, so any application can actually call into it. It doesn't have to be one of the scripting engines. You could have, say, for example, an email client and that wanted to scan emails, or an instant messenger that wanted to scan messages. They could actually query AMSI. So is AMSI something we actually need to worry about as a red teamer? Well, I thought this kind of tweet from Lee Holmes was pretty interesting because it shows the kind of state of play with regards to AMSI right now. So as you can see, there's actually only a handful of vendors that are using AMSI. And if you remember, I said it's only available on Windows 10. So if your target isn't on Windows 10 and they're not using one of these handful of AV solutions, then you might actually not even need to think about it. So let's talk a little bit about some AMSI bypasses. So mid-April last year, Casey Smith released the details on the second iteration of what he called the Squibbly attacks, or called Squibbly 2. This attack basically allowed you to execute scriptlets in full trust when they were embedded inside an XML style sheet using the WMIC command line tool. While I was playing with this technique, what I noticed was that the same SharpShooter payload, when it was embedded inside a scriptlet, wasn't triggering the Defender AMSI signature. This was kind of interesting because what it meant was that after kind of proclaiming the tool to be dead, Casey had actually provided me with a potential technique to resurrect it. With this in mind, what I started to do was incorporate some updates into SharpShooter that used the various kind of Squibbly attacks. So not just Squibbly 2, but also the Squibbly Do original attack, which uses the regserve32 binary with an SCT file. To do this, what I did was I kind of created or coined the phrase com staging. So essentially, there are several known com methods that allow you to run an execution cradle on Windows, and that are accessible to anything that can access com, so something like the Windows script host. So what I did was I basically introduced, I took advantage of some of these com objects, specifically the Outlook create object, which was first documented by Etienne Stallmans at Seventh Post, wscript.run, and the shell browser window run method, which is kind of interesting because that one actually uses the parent processes of Explorer when it executes. So that can kind of confuse EDR a little bit. And the WMI start Win32 process com object. So I use these com interfaces to execute WMIC or regserve32 on the command line to perform one of the Squibbly Do or Squibbly 2 attacks. And this worked reasonably well. So if we look at that kind of workflow, we would have something like a HTA or a JavaScript file, which would use the com interface to call one of these com methods, something like outlook.create object. It would call WMIC on the command line or regserve32. It would then retrieve a remotely hosted style sheet or SCT file online and execute them in memory. And that worked pretty well. As I said, it kind of completely bypassed AMSI. But then I had a little bit of a revelation in that there might be a slightly more elegant way to approach this. What I kind of realized was that if we'd already got access to com, if we could find a com interface that would natively process a style sheet, it might be possible to execute the scriptlet directly from Windows Script Host. And with that in mind, I started to kind of do some research on MSDN, looking for com interfaces that would actually allow you to process style sheets. And one of them, the one that I identified, was the XML DOM interface. This basically had a transform node method that could be used to parse either an inline or remotely hosted XML style sheet and execute JavaScript or VB script in full trust. The main benefit of this over the Squibbly Do and Squibbly 2 attacks is that there's no kind of command line execution. So you get to avoid all the indicators that are associated with those techniques. Also, the payload can actually be very small, so it's quite difficult to distinguish it from legitimate use of this com interface. And I mentioned earlier that AMSI wasn't actually supported in scriptlets, so it wasn't at this time. It gave you full kind of carte blanche bypass for AMSI. Windows did add, Microsoft did add support for that in early 2019. This technique was also used by BOHOPs to bypass Windows Defender application control. So what might an exploit for this kind of thing look like? So here's a very simple JavaScript example, and all it's doing is retrieving in sort of 5 lines of JavaScript. It's retrieving a remotely hosted style sheet, and when it calls the transform node method, it will execute any JavaScript or VB script inside that style sheet in full trust. So that basically allowed us to execute a .NET to JS payload from the style sheet. So if we look at a little example of how this might look. So I'm using SharpShooter to create a JavaScript file, and I'm telling it that the style sheet is hosted on this URL 10.02480 XSL demo up here. And then I'm just going to host both of the files on the Cobalt Strike team server. And I've got a Windows 10 VM with Windows Defender turned on, updated at the time. And if we browse the HTML file, you can see it serves a JavaScript file. The user opens the JavaScript file, and it fully bypasses Defender. And you can see just up here, I'll flick over to it in a second. No alerts have been triggered. We've fully bypassed Defender and AMSI. So as I said, that technique worked reasonably well until Microsoft added AMSI support to scriptlets earlier this year. So let's talk a little bit about some other bypasses that directly focus on AMSI. Well, Tal Lieberman discovered quite a simple little trick. Essentially, there's a registry key that's accessible in the current user hive called AMSI enable. If this key is set to 1, or sorry, it's set to 0, then AMSI is just completely disabled. So with this in mind, what you can do is basically have a small harness that will first check whether the key exists. If it doesn't exist, you write it, and then you just reopen your same payload. And then on the second pass, when you open your payload for the second time, AMSI is completely disabled, and you get carte blanche. So a payload for that might look something like this. So it's a very simple JavaScript file. First checks whether or not the registry key exists. If it doesn't exist, because we tried to read from it, it throws an exception. So when we catch the exception, we write the key, and then we just reopen the script again, and we set it back to what it was. And on the second pass, when we call cscript, it gets full kind of access with AMSI being disabled. So that again, still works today, works quite well. Another AMSI bypass. This one was discovered by James Forshaw. He discovered basically AMSI was susceptible to DLL hijacking. So what James discovered was that it was possible to stop load library from loading the AMSI DLL by convincing it into thinking it was actually already open. The way he did this was he created just a copy of wscript.exe and just renamed it to AMSI.dll, which you can use to, you can still execute on Windows. When he runs the AMSI.dll with the script file, load library would see that that image is already loaded, and it's obviously it wasn't amsi.dll, it's actually wscript.exe, but it would think that it's already loaded, and it would refuse to load the legitimate AMSI DLL. So none of the exported DLL functions would be available. AMSI would fail open, and it basically meant that no AMSI support was available inside that process. Probably one of the most well-known AMSI bypasses is the AMSI scan buffer patch. This one again was discovered by Tal Lieberman. So because the AMSI DLL is loaded into a process that you've already got code execution in, the bypass works simply by finding and patching the AMSI scan buffer function. So this is the function that's responsible for processing and scanning the kind of malicious buffer. And basically you would patch it to return AMSI result clean, which means that AMSI will never actually detect anything malicious. So with this in mind, what I did was I started to add some of these AMSI bypass techniques into SharpShooter. So I'll demonstrate one of them now. So again, similar kind of thing. I'm just creating the initial payload, hosting it on the Cobalt Strike team server. And we've got a Windows 10 VM here where you can see the registry key is not currently set. We browse to the same file, retrieve a malicious JavaScript file and open it. You can see it pops up twice, which is the second pass. And now the registry key is set. There's been no kind of alerts or anything from Windows Defender. And we've got another Cobalt Strike beacon. So again, we've got another kind of full bypass for AMSI. In February this year, I added some additional functionalities to SharpShooter to generate macros. Specifically, I added a couple of new templates. The first one to use the XML DOM technique that I mentioned earlier with VBA. The second one was to add support for XL4. So the XL4 trick was kind of quite interesting. This followed on from some research that was performed by Stan from Outflank. Stan basically discovered that there was a legacy feature of Office that allowed you to execute macro code without VBA. This technique had long really been forgotten about, and the engine for it didn't actually support AMSI, so you didn't really need to worry about AMSI. And a lot of the EDR and AV solutions are based their detection around traditional VBA P code. So again, this kind of got around a lot of EDRs, and we've had a lot of success with it. So to bring this to SharpShooter, I basically added support to generate Silk files. And basically, you can now create a Silk file that will execute shellcode using an XL4 macro. Silk files are particularly interesting because they open outside of Excel's protected view sandbox. So that means that there's there's one less warning really for the user for the user experience when you're targeting them. So I've got another little demo of an XL4 payload. So with the XL4 ones, what you actually have to do is modify the shellcode to not contain any null bytes. So before I do that, I'm just using MSF Venom to do it. And then SharpShooter will use the null byte free shellcode. So again, I'm just hosting this on Cobalt Strike team server. Now we've got Windows 10 VM with Defender and all the protections turned on. So this time we get a Silk file, and when we open the Silk, it opens up in Excel, and the user just gets the standard kind of macro enable content warning. When they click enable content, they get the it runs the shellcode. So as I mentioned, we've had a lot of success with this technique on engagements because a lot of detections that aim to focus on blocking macros are focused around detecting VBA. So let's talk a little bit about tradecraft. So by default, SharpShooter doesn't actually, it's not intended to be weaponized. It doesn't employ any specific OPSEC tradecraft. The version that I released was mainly proof of concept. As such, there are a number of indicators that exist in the default templates that you might want to address before if you're going to use this in a real operation. So these were noted in the analysis that was performed by a number of vendors. So there's two kind of really interesting blog posts from the guys at Countercept, which talk about some of the things that they hunt for and the IOCs that they would hunt for in this tool. Specifically, some of the things that they mentioned are the default templates will, the default payload will allocate memory for shellcode using the execute read write page permission, which means that hunters can just search for these memory permissions in use. It will execute shellcode in process, which means that you might end up having something like MSHDA calling out to the internet to perform your C2. And then it doesn't really do any kind of manipulation of process spawn chains. So what you will have is it will just end up with a default parent. So you could end up having wscript.exe running as a child process of chrome.exe. So again, this is probably an indicator that something malicious is going on. So how can we kind of address these? Well, firstly, just with a couple of extra lines of C#, we can modify the permissions that we allocate for the shellcode. And we basically specifically try and avoid the execute read write permission. So what we would do is firstly allocate the page using page read write. Then we would write our shellcode to it. We would using write process memory. We would then reset the page permissions to page execute read. So at no point have we ever been execute read write. This means if the hunters are searching for execute read write, they'll never find it. It's very simple. We can also avoid some of the process indicators by using injection. So rather than executing shellcode in process, what we can do is spawn a new process, something innocuous that might normally talk to the internet, for example, something like Internet Explorer. We would then inject our shellcode into it using whatever your preferred injection technique is, whether that's set thread context, create remote thread, whatever you want to do. And then that basically avoids something like MSHDA talking to the internet. We've just got Internet Explorer talking to the internet, which kind of blends in a little bit. Finally, we can avoid those pesky kind of parent-process relationships using the PPID spoofing technique. Essentially, when we create a new process that we inject into, we can specify an arbitrary startup info X structure that points to any arbitrary process. So what you would do is first scan for the process ID of something like explorer.exe, get a handle to it, then populate this structure with a pointer to that handle, and then spawn the new process. This works really well. It fools many of the analysis engines, including Sysmon. We've used it to bypass the process spawn relationships and things like CrowdStrike. And it basically fools them into thinking that the parent process is actually explorer.exe. So let's look at a little demo of some of this tradecraft. So I'm creating a payload and then just hosting it initially. And then I'll show on the endpoint a breakdown of what this looks like in Process Hacker. So we've got Defender turned on as normal. And when we open the JavaScript file, Let's just pause that there. What we can now see is rather than WScript or equivalent, we've actually got Internet Explorer running, which is hosting our implant. And Internet Explorer is a child process of explorer.exe. So we've actually fooled Process Hacker, and I mentioned before, this works with CrowdStrike and Sysmon and most of the other kind of analysis engines. We've actually fooled it into thinking Internet Explorer, which is hosting and doing our C2, is the child process of Explorer. And just to prove we've got full kind of C2, I think I'll just flip to Cobalt Strike, and you can see we've got the beacon back. So that's a couple of tricks, techniques that you could use to improve tradecraft. So let's spend a couple of minutes just talking about detection and prevention. So how would we approach actually detecting one of these payloads? Well, if the payload is staged and it's using the code DOM reflection technique that I talked about earlier, you might think that the payload is actually compiled in memory, which is actually what I thought when I was building this tool. The reason for that was there was one of the parameters that I used to pass to the code DOM compiler called generating memory equals true. But that parameter doesn't actually do what you think it does, or what I thought it does. So what it ends up doing is it stores a copy of the C# source code in the Windows temporary directory for a short spell. It then calls out to csc.exe, which is bundled with the .NET framework, compiles it on the host as a DLL, and then loads it into memory. So as a defender, you can kind of monitor for this kind of behavior using things like command line logging, looking for csc.exe, C# scripts getting written to the Windows 10 folder. There is like a way to kind of get around this using the Roslyn compiler. SharpShooter doesn't support that, but it's only available in later versions of the .NET framework. If the payload is using something like DNS delivery, the way the DNS delivery works is it calls out to nslookup.exe on the command line to retrieve text records. The reason it uses this technique for NSLOOKUP is because version 3 of the .NET framework doesn't have a native library to do DNS text lookups. So if you're a defender, you can, and you see, and you've got command line logging in place with something like Sysmon, and you see lots of nslookup.exe being called, then potentially something malicious is happening. As a defender, you can also monitor the registry for modifications to things like the AMSI enable registry key, because this is not really likely to happen on a workstation through everyday usage. In terms of prevention, there are some really powerful kind of prevention strategies. Probably the most effective is quite a stringent device guard code integrity policy. So you can use this to limit script execution to only signed scripts. You could have application whitelisting, which will block things like MSHTA or WScript or CSC. Most users might not necessarily need to run these. You could use group policy to change the default handlers for some of the scripting file formats. So for example, you could associate .js or .hta with Notepad rather than MSHTA or WScript, or just a combination of all these. On the network level, obviously, if you've got DNS monitoring in place, you can look for signs of DNS C2 because they are quite easy to spot. You could monitor for HTML smuggling by detecting files that are using the web crypto APIs, although it's probably prone to false positives. So to wrap up, conclusions. The Windows script host provides quite a few powerful file formats, some interesting opportunities for initial access. If you leverage these with COM, you can harness them using code execution cradles with scriptlets and execution of WMIC, Register32, those types of application whitelist bypasses. Creating weaponized tools can raise some ethical dilemmas, particularly when they get observed in the wild. After I released this tool, Microsoft did a big blog post on real actors that they'd seen using it in the wild. and they used it to actually disrupt 2 particular malware campaigns in June last year. And they also acknowledged this kind of research as providing an opportunity for them to raise the bar in their detections and improve their products. So I do think there are some kind of positives to come out of red team research and red team tooling, because it gives you that opportunity to raise the bar at scale. And then finally, if you are interested in downloading or using one of these tools in an engagement, it's available on our GitHub repo. Just a quick thanks as well to all the people whose research I used or whose tools that I borrowed. I would recommend going following these guys on Twitter because they release a lot of interesting stuff. And I think Stan from the Outflank team, he's got some colleagues here. They're talking this afternoon, so I'd recommend going and listening to their talk as well. Finally, we've got a couple of minutes left for any questions. No questions? Okay. Oh, one question. Someone's waving. Sorry? Yeah, of course I can. There you go. Yeah. Follow these guys. They do lots more interesting stuff than me. Okay. I think I know who this question's from. Do you use Go compiled binaries? Not usually, no, but I can kind of guess which Go fanboy might have asked me that one. Thanks, Rio. No more questions? Okay, thank you very much.